So the second type of inhibitors are uncompetitive inhibitors. These inhibitors can only bind the enzyme when the enzyme is associated with a substrate. So only an enzyme-substrate inhibitor complex can be formed, and this complex is unproductive. So the enzyme trapped in this complex cannot transform the substrate into a product. So the question is, what would happen to Vmax under this condition? What about Km? So instead of deriving all of these equations, I will start to make predictions, and then we will look at the Lineweaver Bark equation and see if our predictions are correct. So first we can compare side by side competitive inhibition and uncompetitive inhibition. As far as the Vmax is concerned, we have seen that with competitive inhibition, as we increase the concentration of S, we outcompete the inhibitor, and Vmax remain unchanged. Now with an uncompetitive inhibitor, as we increase the concentration of substrate, we will increase the concentration of enzyme substrate complex. We will increase the concentration of product, but we will also increase the concentration of enzyme substrate inhibitor complex, which means that a portion of the enzyme will be trapped into a non-productive complex. And this enzyme, in the presence of an uncompetitive inhibitor, will reach a maximum velocity that will have to be lower than the maximum velocity that can be reached without the inhibitor. So we predict a decrease of maximum velocity. So what about Km? Now if we look at the reaction, when we add the inhibitor, the concentration of the enzyme substrate complex will decrease because we have formation of the enzyme substrate inhibitor complex, which means that the equilibrium of the first part of the reaction, when E and S combine to form the enzyme substrate complex, this equilibrium will be shifted to the right, which means that it will lead to an increase of the concentration of enzyme substrate complex. And so it appears as if in the presence of an inhibitor, the enzyme has a higher affinity for its substrate. So we can predict that Km will decrease in the presence of an uncompetitive inhibitor. So if we look at the Lineweaver Bark equation in the presence of an uncompetitive inhibitor, this equation is 1 over V0 equals Km over Vmax times 1 over S plus alpha prime over Vmax. Alpha prime being this constant, which is 1 plus the concentration of the inhibitor divided by K prime I. So first we can look at the slope. So if we compare the Lineweaver Bark equation with and without inhibitor, with and without inhibitor, the slope is the same, Km over Vmax, which means that the straight line for the reaction with and without inhibitor will be parallel. Now if we look at the intercept with the y-axis, without inhibitor it's 1 over Vmax. With inhibitor it's alpha prime times 1 over Vmax. And alpha prime is larger than 1, which means that the straight line with inhibitor will intercept the y-axis, the vertical axis, at a much higher position. That indicates that 1 over Vmax in the presence of an inhibitor is larger than 1 over Vmax in the absence of an inhibitor. That means that, as we predicted, Vmax, the apparent Vmax, which is the Vmax in the presence of the inhibitor, is lower than the Vmax in the absence of inhibitor. Now what about Km? If we look at the Lineweaver Bark equation, we can see that the apparent Km in the presence of an inhibitor equals Km over alpha prime. And because alpha prime is larger than 1, then we confirm what we predicted, is that the Km in the presence of an inhibitor is lower than the Km in the absence of an inhibitor. The last category of inhibitors that we will discuss are called mixed inhibitor. These inhibitors can bind to both the enzyme-substrate complex and a free enzyme. So in a way, they are a combination of competitive and uncompetitive inhibitors. What can we predict for Vmax? Once again, we'll have the formation of an enzyme-substrate inhibitor complex, which is unproductive, which means that the maximum velocity for the reaction with the inhibitor will be lower than the maximum velocity of the reaction without inhibitor. So we expect Vmax to decrease. What about Km? It's complicated. We have formation of the enzyme inhibitor complex. So we've learned from competitive inhibition that will lead to an increase of Km. But we'll also have the formation of the enzyme substrate inhibitor complex. And we have learned from uncompetitive inhibition that results in a decrease of Km. So what will happen is that Km can either stay the same, increase, or decrease. Everything will depend on the relative values of Ki and K prime I. The net effect will depend on the relative rate of the formation of the enzyme inhibitor complex and the formation of the enzyme substrate inhibitor complex. What does the Lineweaver Bark equation tell us? The Lineweaver Bark equation is 1 over V0 equals alpha Km over Vmax times 1 over S plus alpha prime over Vmax, where alpha is 1 plus the concentration of inhibitor divided by Ki, and alpha prime is 1 plus the concentration of inhibitor divided by K prime I. Both alpha and alpha prime are larger than 1. The intercept with the vertical axis will be without inhibitor 1 over Vmax, and with inhibitor will be alpha prime times 1 over Vmax, so it will be a higher intercept, and that confirms that, in fact, Vmax in the presence of an inhibitor will be lower than the Vmax in the absence of the mixed inhibitor. In our example, the inhibitor favors the binding of the enzyme over the binding of the enzyme substrate. So Ki dominates K prime I under this condition. As you can see on the plot, the apparent Km in the presence of an inhibitor will be higher than the Km of the reaction in the absence of the inhibitor. In fact, the apparent Km equals alpha Km divided by alpha prime. We have a very specific subgroup of mixed inhibitor. These inhibitors are called non-competitive inhibitors. They have an equal affinity for the enzyme and the enzyme substrate complex. Under these conditions, alpha equals alpha prime. While it does not change anything for Vmax, now we know that Km, the apparent Km, equals alpha Km divided by alpha prime. Because alpha and alpha prime are the same, then the apparent Km will be equal to Km. So with these non-competitive inhibitors, the Km of the reaction will be the same with and without inhibitors. So we can summarize the effect of reversible inhibitors on the apparent Vmax and the apparent Km of an enzyme for its substrate. So in the absence of inhibitor, we have Vmax and Km. If we have a competitive inhibitor, Vmax is unchanged, Km increases, and the apparent Km is alpha Km. In the case of an uncompetitive inhibitor, Vmax decreases, and the apparent Vmax is Vmax over alpha prime. And Km decreases as well, and the apparent Km is Km divided by alpha prime. With a mixed inhibitor, Vmax will decrease, and the apparent Vmax will be Vmax divided by alpha prime. While the apparent Km can either increase, decrease, or remain the same because the apparent Km is alpha Km divided by alpha prime. So we have covered in this video a lot of material. And if you are interested in the detailed derivation of all the Lineweaver Bark equation that we mentioned here, you can go back to the course website and check equation kinetics document that has been posted. Now, through all of these 6 videos about enzymes, we have learned how we can study the function of an enzyme, how we can make some predictions about the enzyme kinetics. We've defined what will be the impact of inhibitors on the enzyme kinetics. And all of that will be extremely important to help us to understand the regulation of metabolic pathways that we will discuss later in this course.